Is that good? Excellent. OK, well, Andy unfortunately had a family emergency today, so he asked me to take over his lecture. And the topic of today's lecture is the Kerr metric, which was introduced last time, and I absolutely love it. So I'm very happy to be here and be talking about it. So the plan is to go through the singularity structure and the causal structure of the spacetime. Then I want to discuss some special features that are new in the rotating Kerr black hole, such as the ergosphere. And I'll also try to give you some intuition for what happens around the event horizon. There's some qualitatively new phenomena, and those are best understood, I think, by playing around with the equatorial geodesics a little bit, which are mathematically simple but help us build some intuition. After that, I'll briefly discuss the general geodesic equation and how geodesics can be integrated in the spacetime, which is perhaps surprising because it doesn't have manifestly the right amount of symmetry for this to be possible. And then I'd like to introduce the near horizon geometry of the extreme Kerr black hole, which is known as NEC, or the throw geometry, which has very interesting properties that hopefully will soon be observed in experiments. So that's the plan for today. Maybe it's a little bit too much. So if I'm squeezed for time, I'll perhaps skip over the geodesics. A lot of it will be on your homework. So depending on how much time I have, you may have more or less to do on your problem sets. And finally, let me mention there's a public lecture at 6 p.m. in the Science Center by Michael Johnson, who's involved with the EHT. Should be really amazing. I plan to go there. You're highly encouraged to go as well. So we'll have to end a little bit early to give us time to head there. OK, so without further ado, let's get into it. So last time, we wrote down the Kerr metric. And let me rewrite it on the board. So the line element is given by this. OK. So it's quite complicated. Should have written it before class started. It's really amazing that somebody managed to derive this, Kerr. And I think every discussion of black holes should start with this metric, because if you think about it, it's really amazing that we know the space-time geometry around a real black hole in the sky. OK, so this is the full line element. And there are two functions that appear in here which are yet to be defined. One is delta, which is r squared minus 2mr plus a squared. And the other is rho squared, which is r squared plus a squared cos squared theta. OK, so in principle, everything we want to know about the Kerr black hole is contained somehow in this line element. It's deceptively simple. It fits on a line, on a page. OK, on the board, it takes 2 lines. But I think it's fair to say that the full properties of this spacetime are still not fully understood. A simple question, which is actually relevant this week because of the Event Horizon Telescope, a simple question is, how does light propagate in this background? And that's answered by solving the null geodesic equation, which we'll discuss today. And even that problem does not have a fully explicit solution. Of course, in principle, we can put it on the computer, and we can say anything we want about it. But it has a very rich and intricate structure. So we're going to try to demystify this line element. What does it mean? So the first thing to ask is, are there any singularities in the spacetime? Now, if you remember from basic GR, if you pick your coordinates cleverly, such that the event horizon is a hypersurface of constant radius, then, and these Boyer-Lindquist coordinates on Kerr are picked such that this is true, then the criterion for the location of the event horizon is given by this. And the reason for that is that the hypersurfaces of constant radius have a normal vector d mu r, since they're surfaces of constant r. So this vector is normal to them. And the norm of this vector is g mu nu d mu r d nu r, which is G upper R R. And so if you cleverly picked your coordinates such that the event horizon is a hypersurface of constant radius, you can find the location by solving this condition. And in this case, G upper R R is the inverse of this, because this is the inverse metric and this is the metric with lower indices. So this condition is the condition delta equals 0, which has two solutions. R plus minus, this is a quadratic polynomial, so there are two solutions. R plus minus is equal to m plus minus root of m squared minus a squared. Now remember, Andy mentioned last time that this Kerr family of black holes is parametrized by two numbers, the mass and the spin parameter a equals to j over m. So the first thing that we see here is that we had better have a less than or equal to m. This is known as the Kerr bound. And if it is violated, then there is no event horizon, because these radii become imaginary. And so we get a naked singularity. And we think that's not allowed. There are many reasons why. One reason is that there's a cosmic censorship hypothesis that tells us we should believe that naked singularities do not arise. Another reason why, which we'll come to at the end of the talk, is that as the black hole spins up, the region near the event horizon develops a throat, which becomes deeper and deeper. And in the limit, as the spin becomes maximal, and you saturate this bound so that you get an extremal black hole with maximal spin, in that limit, the throat becomes infinitely deep, and so it can't get any deeper. That's another way to say it. And lastly, there's an argument from black hole thermodynamics, which Andy will cover next week, that associates a temperature to a black hole, and the temperature depends on the spin. And when the spin becomes maximal, the temperature goes to 0, and to overspin the black hole would make the temperature negative, which doesn't make sense. So for all these reasons and many others, we think that this bound is respected in nature. So we have these two horizons. The outer one is called the outer event horizon, and it's the actual event horizon of the black hole. And the inner one is hidden behind it. OK, so in the limit, as a goes to 0, this black hole becomes Schwarzschild, which we know. And we know there that there are singularities. But in Schwarzschild, the event horizon itself has a coordinate singularity in the usual coordinates, but you can pick smooth coordinates across the horizon such that the singularity disappears. It's just a coordinate artifact. And the same is true for this event horizon. So even though these coordinates make it seem like a bad place, you can pick smooth coordinates across the horizon, and nothing bad really happens there. So for instance, the induced metric on the event horizon is perfectly smooth. On the other hand, just like in Schwarzschild, where you have a true singularity at r equals 0, there's also a true singularity here that you cannot undo by a coordinate transformation. And OK, there are many ways to see it. So one way to do that, which you may remember from GR, is to compute this so-called Kretchman scalar, which is the contraction of the Riemann tensor with itself. So the expression for this quantity in Kerr is quite complicated. I will not write it down. It would take too long. But the one thing that I want to point out is that it goes like 1 over rho squared. So this quantity is perfectly fine at the event horizon. There's no true singularity. But it diverges when this quantity rho squared goes to 0. And in fact, it does so only there. So this is a signature of the strength of the gravitational field, and the fact that it blows up there tells you that there's a true singularity. And so to understand the singularity of this black hole, we have to understand what this locus rho squared equals 0 really means. Now if you stare at rho squared, you see that it's the sum of two squares, which are manifestly positive. So you can only go to rho squared equals 0 when both r squared vanishes, and a squared cos squared theta vanishes. And since in general we're going to assume we're not in Schwarzschild, that means cos theta has to go to 0. So that means r equals 0 and plus theta equals pi over 2. So what does this mean?
What did you say the name of that scalar was?
Kretchman. Don't make me write it. It's Kretschmann. Kretchman scalar. OK, so let's try to better understand what this means. This is a funny thing. It's not immediately clear what it is. So I told you that when you take the parameter a to 0, the black hole is not rotating. And so you end up in Schwarzschild in the usual coordinates that we know and love. But what if you keep a non-zero and take m to 0? That's a funny thing to do. Because if you do that, then the black hole has 0 mass, so it really vanishes, and there's no black hole left anymore. So you expect to get flat space. But there's a parameter a that's left there. So what is that? So when you take, in the limit as a goes to 0, the above line element goes to, yes?
If you take r to 0, what does it mean to talk about theta?
I'm about to explain this. That's a very good question, and that's what I'm trying to explain. Very good. So when you take a to 0, the line element degenerates to this. This is the usual round metric on the sphere, d theta squared plus sine squared theta d phi squared.
Sorry, a to 0 or m to 0? Because you're writing a.
Thank you. Sorry. M to 0. Thank you. Yeah. So the idea is I make the black hole vanish by taking its mass to 0. And so I expect to end up with flat space. And indeed, I do. So this line element, you can compute its Riemann tensor. It's identically 0. There's no curvature in this space, so it's perfectly flat. But these are funny coordinates. And I think they have an official name, which are ellipsoidal or elliptical coordinates. I'm never sure what the difference is. Anyway, the point is, if you want to go to the usual Cartesian coordinates, to recover the usual flat Cartesian coordinates in Minkowski space, you can do this coordinate transformation. I apologize for my handwriting. If anything is unclear, please let me know. I'll rewrite it. OK. So you can check if you do this coordinate transformation, then this metric goes to the usual Cartesian set of coordinates on Minkowski space. So what do we learn from this? Well, now we can ask, what is this locus in terms of these coordinates? And what we learn is that this locus corresponds to x1 equal to a times cos phi, x2 equals to a sine phi, and x3 equal to 0. So the singularity, which arises at rho squared equals 0, is really a singularity that's traced out by a circle in the equatorial plane, that is to say a ring. And so the singularity of this black hole is a ring singularity. So in Schwarzschild, the actual singularity is at a point, which is the origin. When the black hole spins, it's sort of smoothed out or resolved into a ring. OK? So now that you know this, in principle, you can figure out everything about this setup. And all I want to say is that you should convince yourself at home that what's really going on here is that you have these lines. These are lines of constant theta. And the lines of constant radius, OK, my artistic skills are about to be tested, look like this. So these are lines of constant radius. And so the locus r equals 0 is this disk in the equatorial plane. So this entire disk here is r equals 0. And then these 2 points are theta equals pi over 2. So the singularity is that ring. OK? Does that make sense? So we asked, where is the metric truly singular? We used this scalar as a measure of that. We found the locus of the singularity was rho equals 0. And by writing the metric in Cartesian coordinates, we determined that it was a ring-like singularity. Does that make sense? And I think, Shruti, does that answer your question? Good. OK, so that takes care of the singularities. Check. Now let's move on to the causal structure. So to get the causal structure of the spacetime, I'm going to write down the Penrose diagram. Now, if you remember from your homeworks in first semester GR, deriving Penrose diagrams, actually deriving them is a laborious task, which requires you to find coordinate transformations to nice coordinates in which the metric is compactified. You've compactified the spacetime, and you've put the metric in a conformally flat form. This is very difficult and time-consuming. And in fact, for Kerr, because the metric depends on where you are, what angle theta you're at, Penrose diagrams are not quite as good as what we usually do in spherically symmetric spacetimes. So remember that if you're in flat space and you write the usual Minkowski diagram x1, t, then really every point on your Penrose diagram is a sphere. So really, you're suppressing a whole sphere. And for flat space, that's OK. And in fact, for every spherically symmetric spacetime, like Schwarzschild or Riesen or Nordstrom, that's also fine. But in Kerr, the actual metric varies across the sphere. So when you suppress the angular dependence on the sphere, you're losing some information. So I think that's another reason, aside from the fact that it's very laborious, why it's not so interesting to try to actually use the coordinate transformation. So I'm just going to skip to the answer and give you the Penrose diagram without properly deriving it. But I should note, this is important, there's always a trick to get to the Penrose diagram without actually always doing the hard work. And so I'm going to use this trick. So what is this trick? Well, we're going to pick constant t, theta, phi surfaces and vary r. And then we're going to see what happens. And we're going to see that when r is between r plus and infinity, we get space-like curves. When r minus is less than r is less than r plus, so when we're between the two horizons, so this is outside the outer event horizon, between the two horizons, we're going to see that these surfaces of fixed r are time-like curves. And I should say, this is not immediately clear. You see, we wrote the coordinate r as though it's a radius. And radii always end at r equals 0, right? But remember, this is gr. So these coordinates don't have any intrinsic meaning. And in fact, one thing we learned from this exercise is that unless you hit r equals 0 at theta equals pi over 2, so you hit the ring, in which case you hit the singularity, in principle, nothing is stopping you from passing through r equals 0. And so when you do the Penrose diagram, when you draw the Penrose diagram, you have to understand the entire causal structure of the spacetime. So you have to maximally continue all coordinates as far as you can. That's called a maximal analytic continuation. And so unless you're at theta equals pi over 2 at every other angle, there's no problem with taking r negative. So in fact, r can go to minus infinity. You have to cover the whole range. That's called the maximal analytic extension. So we should also consider this. And here we find, again, that the surfaces of constant r are space-like. So now, maybe it's not completely clear what I mean by this. What I mean is, if you take constant t, theta, phi, you get an induced line element. And now I'm saying if you vary r, that traces out a hypersurface, is the sign of ds squared positive or negative? That tells you whether it's space-like or time-like. And in fact, this is a good trick for drawing Penrose diagrams, because usually that's kind of all that you need. So now we have everything that we need to draw the diagram based off of this information. And so here goes. So we're going to have, maybe I should draw it here. So let's take scri plus, which is asymptotic null infinity, scri minus, which is asymptotic past null infinity. This is where light rays come from. This is where null light rays go. This is I0, which is spatial infinity. And if I was just in Minkowski space, I would close up this diamond, right? This is the usual Penrose diagram for Minkowski space that you've all seen. But now, instead, there is an event horizon. And the event horizon is at R+. OK? And now, OK, I'm not very good at drawing, so this is rapidly going to degenerate. But the point is that the surfaces of constant radius look roughly like this. So this is a little bit of a cartoon. But the point is that surfaces of constant r are space-like. So that's what they look like here. But now, once we cross r+, there's another radius behind it, r-. And there, the coordinates, the surfaces of fixed r, have the opposite sign. Did I get it exactly backwards?
Yeah, exactly.
Yeah. Thank you. I heard whispers. Sorry. OK, the words doesn't matter. This picture is what really matters. And you can infer that from the sign of d squared. So it looks like this. So this is now r-. OK, this is I+, where time-like particles go into the future. So spatial future infinity, I-, which is spatial past infinity. This is the outer event horizon. Now here you're past the event horizon into the black hole.
Sorry, Alex. Constant P outside R plus has to be space, right? They have constant P, right?
So when I'm outside, I'm at fixed t. It's space-like. Yeah. So it was right before. OK, sorry.
It's just about switching from line to surface.
Yeah, sorry. I talked about surfaces and then I drew lines. OK. Sorry about that. The point I want to make is here, if you sit at fixed radius, you're on a time-like trajectory. That's what I'm indicating here. I talked about two different things. OK. And now, you're not completely done. You have to keep going. And so you have to maximally extend the space-time. And the way it looks in the end is like this. So let's see. There's another r+ here. This is r-. These are the surfaces here. Here they're like this. OK. And then this pattern repeats at infinity. So exactly the same thing here. You can keep drawing down. So there will be another diamond. This will be r-. This will be, these lines are r+ and r+. Here we have another scry+ and scry-. And the lines are the same. So like this here, like this here. OK. And then here, if you're in the equatorial plane, this is r = 0, and you hit the singularity. Wow, I'm sorry, this is very bad. I have one that's latex, so I'll put it up online, and I'll put it up on the screen in a bit. So if you're at theta = π/2, then the singularity is present, and so you can't go past r = 0. If you're at any other angle outside of the equatorial plane, then you can continue past the singularity, and there's another patch here, and this is where the negative radii are. OK? So the idea is you look at all the patches of every radius. the radii can be negative, which is a little bit weird, but nothing stops you from doing that. It's the maximal analytic continuation. You look at all these regions. You ask, are these surfaces of constant r? OK, here I drew the word lines. Are they space-like or time-like? You draw this, and then you have to always make sure that you maximally extend. This diagram can only ever end on scry or at a singularity. Yes? Exactly. Good. So that's the next point. I'm getting like perfect questions. It's as though like I planned it. Yeah. So OK, what's the interpretation of this? OK, this is very weird. So let me stop drawing bad pictures, and let me say a few words about what this means. Wow, this is really bad. I'm sorry. Let me. Well, I'll project it before the end of the class. So if you want a better picture, you'll see that in a second. But the point I want to make is that in principle, you can start here, which is outside of the black hole. And you can follow a time-like trajectory. So remember, a time-like trajectory, which is an allowed path, is one which never has an angle of more than 45 degrees, because that's the angle that light travels at in these coordinates. So you can start here. You can cross r+. So you can start at some large radius, near infinity. You can cross the outer event horizon of the black hole, r+. You can go through, and you can avoid the singularity, go through r-, avoid the singularity. Just keep going, and in principle, you can come out after you pass through the interior of the black hole to the other side, which is like a different universe. OK, this is very weird. I think it's very important to say that if you have a black hole which is formed by gravitational collapse, so you take a shell of matter, you collapse it into a black hole, then you can show that only the region with positive r exists. In other words, this entire region with negative r, it doesn't really exist. So this is only an artifact of the exact perfect mathematical solution describing the eternal black hole. And I think it's a little bit of an open question how seriously one should take this. I mean, the real black holes formed by collapse only have the one patch. There isn't another universe beyond. But maybe there's something in this math hidden here that's trying to tell us a clue as to what's going on. Yeah.
Sorry. The way you've drawn it, the negative r only exists on those little half triangles, on those little triangles on the outside of the singularity.
Yeah.
Like, which has nothing to do with the path dimension of going between universes. So whatever theorem you're talking about is more than just like the negative r doesn't exist. It's that like something about like if you start out with like something that's like asymptotically Minkowski in time, and you have like the collapsing cloud, like you wouldn't have the previous or future universes, right? Like it's got to be more about more than just negative r.
Yeah, does it stop at r minus rather than 0?
No, I mean in the physical case, you'd get a singularity somewhere, right? You'd get a curvature singularity somewhere. So it should go to r equals 0.
Well, it's only in the equatorial plane.
Yeah.
So yes, that's true. I'm not completely sure. One thing I can tell you is that I don't think anything can really cross r- in the real world. So I think it stops at r-. I'm not quite, I don't really recall the argument for that. I'll have to get back to you. OK. Let me say one other funny thing about this region of negative r. Where should I say this? Maybe here. So there are closed time-like curves, CTCs. And that's the last thing I want to say about the causal structure. So these are really problematic and may violate causality. And so I think real black holes definitely don't have r negative for that reason. So if you consider the curve, which is at some fixed r, that we take to be epsilon, a small negative quantity. And then we stay in the equatorial plane, and we take t to be a constant. Then the metric along this curve, you can check, is given by 2m a squared over epsilon d phi squared. And this coordinate phi is a compact coordinate. So if you go around in phi, then you get a closed time-like curve. I think that's the argument for why. That's one of the reasons why you can see that black holes that are actually formed by collapse don't have R negative. And in general, the formation of closed time-like curves from smooth initial configurations is not allowed by Hawking's chronology protection conjecture. So there are many conjectures about what can and cannot happen, and this used to be a huge subject in general relativity, which I think Penrose and Hawking, with their singularity theorems, really understood. And so, you have some smooth initial state of data. You let it evolve. What happens? What is allowed to happen? What cannot happen? What must happen? There are all these theorems that constrain that. And the formation of closed time-like curves is believed to be something that's forbidden based on various arguments. And so R negative should just not exist for real black holes. Yep. Yeah, epsilon is negative. That's right. OK. Is there a way to project something over there while leaving the screen free?
Yeah, there's a screen on there.
There is a way to do that, right? Yeah. So is it called left screen?
Maybe it's called right screen.
Ah,
And you like press something and there it came down
Nope.
by accident.
Not this one. It's too big.
Oh, there.
OK. Well, this room is really something else. OK, good. All right. So I sort of anticipated my drawing skills would be abysmal. So pulled up a diagram of the Penrose of the causal structure, and I'm going to leave it up there if I can. It's warming up. All right, well, while it does this, I'll get back to it in a second. It's so amazing, I don't know how to use it. OK. How do we turn the lights back on? OK. Can you help me for a second, please? Do you know how to turn the lights back on here?
No.
Let's see.
I think it's
That's
a
off.
button on here. Oh, okay, got you.
Sorry. OK, while this is happening. OK, so we'll leave the causal structure displayed. Thank you very much. Sorry to make you get up. All right, so let me talk about the next topic, which is the ergosphere. And now we're getting into some of the really cool physics of the Kerr black hole. So let's see. What can I erase? Maybe I should go here. OK, so the Kerr solution has a special region outside the horizon, which is known as the ergosphere. And this is a region in which a particle can have negative energy, but it's still possible to escape from this region. And so that allows for very interesting phenomena. For instance, spoiler alert, interstellar. When the spaceship doesn't have enough energy to get to the distant planet that they need to get to save mankind, they have this like throwaway sentence in the movie where they say, oh, we'll slingshot around the black hole to get enough energy to reach the planet, but then Matthew McConaughey has to sacrifice himself by jumping into the black hole. OK, so Uh, Andy really wants to do this derivation himself, so it'll be next week. But there's something called... He used to throw graduate students into the black hole. I think now it's Matthew McConaughey. So it's possible, because there's negative energy in the ergosphere, it's possible to go to that region, from which, again, you can still escape. And you can drop something on the trajectory with negative energy. So you lose negative energy, which means you gain energy. And then you can get out of that region, and you have more energy than you had coming in. So that's how, by sacrificing Matthew McConaughey, you can save mankind. And Penrose, in his original paper, where he described this mechanical Penrose process, how with particles on geodesics you can achieve this, which will be covered next week. At the end, he himself wrote, oh, this is like a very interesting fact, but it would be really interesting to understand the electromagnetic analog, because we know there are magnetic fields around the black hole, and if they get into the ergosphere, can these magnetic fields extract energy from the black hole? And this energy, of course, is not magically stolen from anywhere. It comes from the spin of the black hole, which as a result rotates more slowly. And in fact, it's now, I think, commonly accepted that these quasars, which I spoke about last week, which are the brightest lights in the universe, are caused by these jets that are shot out by black holes near their poles. And the commonly accepted explanation for what powers these jets is known as the Blanford-Znayak mechanism. It's kind of an involved story, but it involves using this fact that there's negative energy in the ergosphere, and the magnetic fields are the ones that are sucking the rotational energy of the black hole and using that to power the jets. So there's a lot of really interesting physics. So that was just to whet your appetite. So we're going to start basic. So we're going to now consider curves of constant r, theta, and phi. And we're going to vary t. So the line element along such a curve is ds squared equal to minus 1 minus 2 mr over rho squared dt squared. And this curve is time-like if 1 minus 2 mr over rho squared is positive. So rho squared is displayed still over there. So that means it happens if r is greater than rs plus, or r is less than rs minus, where these guys are the roots of rho. Which are given by this formula. Now recall that r minus, r plus minus, the inner and outer event horizon are given by that formula. So that means that you can see from this that rs minus is less than r plus. So this is beyond the event horizon, so we're not going to care about this too much. But on the other hand, this is greater than or equal to r plus. And so therefore, this region is accessible to an outside observer. And in fact, we can draw where in space this is located. So the event horizon is the surface of fixed radius r equals r plus, which is supposed to be this circle. And the locus of r theta, so this is a cross section of the so-called poloidal plane, so the r theta plane. So this is a sphere, the event horizon. And this locus has this shape. So I was looking at the textbook, Carroll, earlier today, and I was a little disappointed. The discussion is very good, but he draws the ergosphere like an ellipse. So if you plot this, it looks like an apple, not like an ellipse. Of course, it's not a grievous offense, because in GR, these coordinates don't mean anything. I think it's very important to emphasize we pick coordinates where the event horizon is at constant radius because that's convenient. But the event horizon is not a sphere. As soon as the black hole spins up, the induced metric on the horizon is not that of the round sphere. It's warped. So this is just a choice of coordinates. There's nothing. It's convenient, but it's not physically meaningful. But it's useful for us to draw a picture of what happens. So you have this ergosphere. And now I'm going to draw as a cartoon what I was saying before. You can come in from outside. You can drop something on a negative energy trajectory with your spaceship, and then you can come back out, and you have more energy than you had going in. That's the cartoon picture of the Penrose process, and I think Andy will work it out in detail next time. Now, this surface is known as the Ergo Surface, and it bounds the Ergosphere, which is this region between the Ergo Surface and the event horizon. So that's the Ergosphere. And inside of the Ergosphere, these curves of constant r, theta, phi, but varying t, are space-like, which is a little funny. And moreover, all geodesics that are inside the ergosphere must co-rotate with the black hole. So one physical way to understand what this region means, yeah, maybe I should say that. So the event horizon intuitively is the place that once you cross into it, you can't come back out. The ergosphere has the property that you can cross into it, and as long as you're here, you can still get back out, but it becomes impossible for you to remain at fixed angle. In other words, you have to co-rotate with the black hole. And I'm going to prove this to you by analyzing equatorial geodesics. And it's actually really cool how it happens. So let's work through that. Where's the erase? OK, so let's consider a geodesic at fixed r and theta. So the line element along the geodesic is ds squared equals minus delta over rho squared dt minus a sine squared theta d phi squared plus sine squared theta over rho squared r squared plus a squared d phi minus a dt squared. OK? And we're going to set theta equals pi over 2 for simplicity. And this is a trick. So usually to solve the geodesic equation, you have to derive it and do a bunch of stuff. But now we're going to use a trick, which is that a null geodesic will be such that ds is 0 along its path. And so if you set ds equal to 0 to get a null geodesic, then you'll find, by solving this equal to 0, you'll find that d phi dt is equal to a plus minus root delta over r squared plus a squared plus minus a root delta. OK, and so we can analyze this in detail, but I just want to note 3 different cases that will help us build intuition. So one, the first case, is r much, much bigger than this, so very far away from the ergosphere. So if we're there, then this equation tells you that null geodesics satisfy d phi dt is equal to plus minus 1 over r, which is the expected result in Minkowski space. So if you were to study light rays in flat space, and once we're very far away from the black hole, we're basically in flat space, we had better recover the Minkowski space result, which is this. And this describes, light-like trajectories that are going clockwise or counterclockwise around the origin. OK, so that's basically the flat space result. But now let's move in and start to probe the curvature of the geometry. And what you find is that at r equals rs plus, which is the ergosphere, and it's a 2m because I put us in the equatorial plane, then we have delta equal to a squared. And so this thing tells us something a little bit funny. there are two solutions. So remember, the plus sign or minus sign means whether you're going clockwise or counterclockwise. But once you hit the ergosphere, you find that the two solutions become d phi dt equals 0, or d phi dt equal to 2a over r s plus squared plus 2a squared. Somebody please check my algebra. I hope I'm doing this right. I think that's good. So what does this mean? Remember, in flat space, if you pick a point, then you can draw the light cone emanating from that point. And it's bounded by two light rays, the one that's going to one side and the one that's going to the other side. That's the flat space picture. What this is showing is that if you move this point closer to the black hole, once you get to the ergosphere, the light cone is tilted. So the light ray that you want to emit to one side is actually not able to counter-rotate. It's at fixed angle. And the other one is co-rotating with the black hole. So you can't have a geodesic that's maintaining a fixed angle, because you can't have a massive geodesic maintaining a fixed angle, because this is the place where even light that's sort of counter-rotating with the black hole is actually stuck in place at the same angle. OK, I think that's a better way to say it. So you imagine shining a light in the opposite direction of rotation of the black hole. And here it's OK, it's OK, it's OK. And once you get here, the light is frozen at fixed angle. And once you go in deeper, it actually, even the counter-rotating light is actually going around with the black hole. Does that make sense? Are you unhappy? Is there somebody unhappy? OK, so if even light here is forced to co-rotate, because if you're massive on a time like geodesic, you can't go as fast, then it's clear that you're forced to co-rotate. That's the argument. OK, all of this can be made very precise, but I think this is the fastest way to get to those statements in Bill intuition. OK, so the conclusion here is that only null light rays can remain stationary on the Ergo surface. But once you get inside, then, but still outside the black hole, you get this phenomenon of frame dragging. So the picture that you should have in mind here is that if you remember the trampoline analogy of gravity, that gravity creates a depression in the fabric of space-time when there's matter or energy there. Here this is telling you that the matter, if it rotates, will actually also drag the fabric of space-time around with it. So this phenomenon is known as frame dragging. OK, so it's law of physics that once you're inside the ergosphere, you have to co-rotate with the black hole. And finally, what happens once you reach the horizon? That's the third case I want to discuss. Then something funny happens. This is even funnier. So you can see that the two solutions to the equation actually coalesce. And you find that d phi dt is equal to a over r plus squared plus a squared, which means that the light cone has closed up. OK? So usually in flat space, you can send a light ray this way. You can send it this way. At the ergosphere, it's tilted. You can only go one way. And once you get to the horizon, there's only one direction, and the light cone has completely closed. So everything is forced to co-rotate with the black hole at this with this angular velocity. And of course, time-like geodesics can't achieve this. So there are no time-like geodesics at fixed radius equal to r plus. They have to terminate before. And if I have enough time, which I may not have, I'll derive the radius where the time-like geodesics at fixed radius end, which is known as the ISCO and is relevant for a lot of accretion disk physics. OK. Now, this is independent, in fact, of the angle theta. I'm only doing the equatorial case here, but you can do the analysis in general. And so this thing tells you that you can think of the event horizon as spinning with this angular velocity. And so this quantity is known as omega h, which is the angular velocity of the horizon. Because the horizon is a null hypersurface, it's ruled by null light rays. and they're all co-rotating with this speed. So you can think of this as the intrinsic speed of rotation of the event horizon. And explicitly, that's j over 2m times m squared plus m fourth minus j squared, the minus 1. So at extremality, when the black hole has maximal spin, so a goes to m and j goes to m squared, this goes to 1 over 2m, if I didn't mess up. Okay. Now, why can the energy become negative here? That's the last thing that I've claimed but that I have not shown. The reason the energy can get negative here is because the time-like killing vector d by dt, which generates the symmetry of time translation, gives particles an energy. So if you have a trajectory parameterized by some x mu of lambda, geodesic or not, you would say that the energy of this trajectory is minus d by dt mu x mu. But the point is that this guy is not globally time-like. So if you compute its norm, dt mu, you find that it becomes, it's no longer time-like inside the ergosphere. It becomes space-like. So the direction of moving forward in time gets space-like, and that allows you to have negative energy. Yeah. Okay, let me write it this way. So let me define k to be dt. I meant k mu, k mu. Sorry, x dot mu. Yeah, thank you. The momentum, p mu. Yeah, very good catch. Thank you. Okay, so how am I doing on time? That's 1 hour. Okay, let me turn the screen on. Blop, 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 blop. Wall laptop. Would you mind helping me figure it out how this works? How do I turn on that screen? I have to do. Okay. No. Okay, I'm gonna give up.
Display and screen controls, and then you can like pick which one you want, the right screen, not the left screen.
Thank you.
Yeah.
Okay, and then this one is on. It should be on though. Okay, it's not worth it. Can I use HDMI to project something over there?
Yeah, it should.
I'm sorry, I should have familiarized myself, but I thought I would do this on the fly. Okay, are there questions about anything I've said so far? While this lights up. Yeah, Adam.
Why do you expect it to have any null geodesics for fixed radius? Go for like a circle around the equator. Like it sounds really weird to me to generically have a light ray that can go in a circle.
It can only happen between two radii, which are called the photon orbit, prograde, retrograde, and this will be on the homework. So you're going to have to derive all of this.
So then, how do we have solutions to this for the Fulmers radio? Oh, we were just solving null. We weren't necessarily saying geodesic mathematically.
Right, I was looking at null trajectories of fixed radius. They don't exist. They're not geodesic for every radius r.
Yeah, you wrote geodesic.
Yeah. Sorry. Okay. Now, let's see, how am I doing on time? All right, let me say something about the geodesic equation in general and how you derive it, because there's something interesting about this. So, okay. You know, and this was the promised, let's see, does this work? Okay, so the Penrose diagram that I was trying to draw is the one on the left. Okay. All right, and now I'll explain what the other two are in the last part of the discussion. Okay, so let's discuss geodesics a little bit. So normally, I think in this class we would stop at equatorial geodesics because those are sort of easier to understand. You can do a lot of, you can study them analytically. But now that we have the first image of a real black hole in the sky, and we're getting a lot of light from all around the black hole, I think it's a really good time to grapple with the null geodesic equation in its entirety. And on the homework problem that will be assigned to you today, you'll be asked to derive a number of facts about null geodesics in the Kerr spacetime, not just in the equatorial plane. And so I just wanted to take a little bit of time to explain why, even in principle, that's my alarm to make sure I don't go over time. I wanted to explain why, even in principle, you'd expect to be able to study the geodesics analytically. So without getting lost into the weeds, you might remember from classical mechanics that if you have particle motion in n dimensions, then it's completely integrable in the sense of Liouville's theorem if and only if there are n conserved quantities. So in other words, whenever you have a dynamical system that has a phase space that's 2n dimensional, there are n space-time coordinates. If you have n conserved quantities, then you're golden, because you can describe the motion just using the conserved quantities, and there's enough symmetry, enough conservation laws to completely characterize the motion just using that. And this turns out to be the case in Kerr, but it's not at all obvious. It's really sort of a miraculous property of Kerr, which was discovered by Brendan Carter. And it's what makes possible the analytic study of the geodesic equation, where we can write nice equations at all. And it's also why we can separate the wave equation and study perturbations of the spacetime, whether for a scalar field or even gravitational perturbations. All of these facts, all of these nice things we can do follow from a single magical fact, which is that there's extra symmetry in Kerr. So let me make this a little bit clearer. What do I mean by this? Well, I'm just going to sketch this very quickly and not go through it in detail. But the null geodesic, the geodesic equation is the statement that you have a particle whose momentum obeys the geodesic equation, which in momentum form can be written in this way. So the momentum is parallel transported along itself. That's what this equation means. And then there's a mass shell condition that fixes the invariant mass of the particle. So this is the geodesic equation written in terms of the momentum. And in general, if you have to solve this, it's quite complicated. You get some second-order differential equations, because there's a derivative here, and p itself is the derivative of the position. So this is really a second-order differential equation. And in general, it's actually a coupled system of second-order PDEs. It's not very nice. You can put it on the computer and solve it. It's fairly straightforward, typically. But if you want to go farther analytically, it's not obvious that you can. So the strategy is to find symmetries. So if you have a killing vector k mu, then it obeys the killing equation, which tells you that the divergence of k symmetrized is equal to 0. And I'm not going to go through this, but it's very easy. It's only a couple of lines. You can convince yourself that if you have a killing vector k mu and a solution to the geodesic equation, which has a momentum p mu, then the quantity k mu p mu, which is a scalar quantity, is constant along the trajectory. Okay? And the way you can prove this, okay, there are many ways of doing it, but you want to show that the Lie derivative along the geodesic of this quantity is 0, and that's really p mu del mu k nu p nu. And okay, if you just expand this out, use the chain rule, use the geodesic equation, and then this, you immediately get that it's 0. It's just one line. Okay, so this is the statement that if you have a symmetry, which is generated by some Killing vector, then it gives you a conserved quantity along a geodesic. So for Kerr, we have two nice Killing vector fields, dt, which tells us that the metric is stationary, and d phi, which tells us that it's axisymmetric. So now we get two conserved quantities for free. So given any solution to the geodesic equation with momentum describing a particle whose trajectory has a momentum p mu, if we form the contraction dt mu p mu, we'll get a conserved quantity, which we call the energy. And if we take d by d phi mu p mu, we'll get a conserved quantity, which has the interpretation as being the angular momentum around the axis of symmetry of the black hole, so the black hole spin axis. Okay, so now I have three conserved quantities. I get two from the symmetries, and the third one is the invariant mass. But the momentum p mu has 4 components. Okay, so I'm in 4 space-time dimensions. If I had 4 conserved quantities, that would give me 4 constraints on p, which would allow me to solve for the components p mu algebraically and reduce the geodesic equation to a first-order equation only for p mu. If you can do that, then it's basically guaranteed that you can solve the equation because it's integrable. It's solvable by integration by quadratures. Anyway, it's a nice system. But for now, I only have 3 symmetries. So what do I do? Okay, it turns out we rarely talk about this except in this context as far as I know. But it's a very nice feature of Kerr that it has an additional symmetry. So is there an extra Killing vector? No, that's not what I mean. It turns out you can generalize the Killing equation to not just vectors, but arbitrary tensors of any rank. So if you have a rank p symmetric tensor k with p indices, and it obeys this equation, then it's a rank p Killing tensor. So this is just the Killing equation generalized to apply not just to vectors, but to higher rank tensors. Okay, so the simplest thing you can do is ask, are there other Killing vector fields of Kerr? The answer is no. Okay, what about the next level of symmetries? What about a rank 2 symmetry? Is there a rank 2 tensor which obeys this equation in Kerr? And the answer is yes. Now, I have to be clear. If you have 2 Killing vector fields, k1 mu and k2, then if you take their outer product, this is now a rank 2 tensor. You can symmetrize it. Okay, you can trivially check that this will also obey the Killing equation. So you can form, if you have Killing vector fields, or in general Killing tensors of some rank, you can always form higher order symmetries by forming Killing tensors of higher and higher rank. But those are called reducible. So if you can decompose a Killing tensor as an outer product of lower rank tensors, it's not really a new symmetry. You're not learning anything new. So the question is there a new k mu nu, which obeys this equation, which is a rank 2 tensor that's a symmetry, which is not of this form? And the answer is yes, it's unique. And then it turns out there are no other ones of higher rank. So this completely exhausts the symmetries of Kerr. And so the last one I'm going to write down has an expression which is written most conveniently in this way. So it's written as the contraction of a rank 2 antisymmetric tensor, which is a form. And because it's a form, we can write it in this way as a form. Okay, so this is a messy expression. Draw it down. Okay, so this is some nasty expression. I don't expect you to necessarily absorb it, but I'm just giving it to you. So this is a 2 form, so it's an antisymmetric rank 2 tensor. You can form this contraction, and the claim is that you get some k mu nu, which is a killing tensor because it obeys this equation, and it's irreducible, so it's not made up out of dt and d phi. Okay, so this is a magical fact. I think many people have tried to explain where this comes from. Certainly, once you know this, many of the special magical properties of Kerr follow. You can separate the wave equation. The reason you can separate the wave equation, I'm not going to go into this. It's a long story, but that's because the Laplacian, which is g mu nu del nu, commutes with another operator, which is del mu k mu nu del nu. So these two operators commute. And this is enough to ensure separability of the wave equation, for instance. Carter understood this first, I believe. But here what we want to use it for is to describe geodesics. And the reason it helps us is because just like when you have a geodesic with momentum p mu, you take the contraction with the killing vector and you get a conserved quantity, the exact same thing here is true. So if you define a conserved quantity k, which is the contraction of this tensor with your geodesic momentum, you can just take the Lie derivative along the geodesic, and you find that this quantity is conserved. So you act with this operator on this object. You use the geodesic equation to kill p mu, and then you use this killing equation to kill k, and you find that this object is conserved along the trajectory. So this is another conserved quantity. It's a number which is conserved along the geodesic, and I'm going to give it to you explicitly. It turns out that people really like to use something else called the Carter integral, not the Carter constant. It's defined in this way. Now, the energy and angular momentum are conserved. If this thing is conserved, so is this thing. It's just that it has a nicer expression, which is p theta squared plus a squared times mu squared, the mass, minus pt squared. So that's the energy squared, cos squared theta, plus p phi squared, cotangent squared theta. OK, so this is the mysterious fact which is used in your homework that you'll receive today that allows one to separate the geodesic equation. So why is that? I'm not going to work through it because it's complicated. But the point is, p mu has 4 components. And I just gave you 4 constraints. I told you that p squared is minus mu squared. This is true, and this is a 4th condition. So now I have 4 algebraic conditions on 4 components p mu. And you can use this to solve the geodesic equation, by which I mean it follows by solving all these guys that p mu dx mu is equal to minus e dt plus or minus, depending on which direction you're going, a radial potential dr plus minus an angular potential d theta plus L d phi, where curly r of r is equal to e times r squared plus a squared minus al squared minus delta k plus b squared r squared. Okay, so you can get the form of the momentum by solving for these 4 components p mu from the fact that you have 4 constraints on the components. Does that make sense? Okay, it's algebraically involved. I'm not going to do it, but this is the answer. And once you have that, this just tells you the tangent direction to the geodesic. So now you can just integrate this vector field, and the flow of this vector field tells you the direction of the geodesic motion. So now it's just basically come down to an integral, and that's what we mean by it's integrable. Okay, so on your homework, you'll be asked to verify various properties of these geodesics. So the simplest thing that you can see is that if you want, for instance, a circular geodesic, which is at fixed radius r, then you want r of r, the radial potential, to vanish there. That's the statement there's no radial momentum PR that's pushing you away. But you also want the first derivative to vanish. You don't want it to just be instantaneously 0. You want there to be no force pushing you away from that radius. So these 2 conditions, for instance, are the conditions that you would solve. You would solve for the conserved quantities that would describe geodesic motion at fixed radius. Does that still make sense, or have I lost people? Okay.
Delta here, the same delta that appeared before.
Yes. Yes. Yes.
Do you know in what sense killing tensors are symmetries? Like, they have some variation associated with them?
The definition of symmetry is this. They obey the Killing equation. I mean, they give you a conserved quantity.
Yeah.
So
Yeah,
there's a lot more that, I mean, people have written many, many papers about this. There's a ton you can say, but I think for my purposes, that's all I've ever had to use. But yeah, there's something called killing Yano, killing Steckel tensor. It's a huge thing. All right, so let me show you some equations that I don't want to derive, but I just want to flash them by you. This is standard material. So there's a 1972 paper by Bardeen, Press, and Tucholsky. Oh, that was supposed to show up here. Can I do this? So these gentlemen in 1972, this is a classic paper, which is an excellent reference. And if you want to learn more about this, I urge you to read it. This is the place I go to. These gentlemen started here and then basically figured out everything. So the formulas are pretty gory. I'm not going to take the time to write them on the board, but I'm just going to show you some salient points so that you understand the logic. So they start with the Kerr metric, as we did. They talk about the horizon and the ergosphere. You can see where I drew inspiration from. They tell you that there are these 3 conserved quantities, EL and Q, which is what I also told you. And then they use that to solve for the 4 components of the momentum vector P mu. I wrote it in lowered form, so I wrote P lower mu. Here they give you the components P upper mu. These are just related to what I drew on the board by acting with the metric that raises the index. And then they say, for instance, if you want to be at fixed radius, you impose these 2 conditions. Okay, they used V for the radial potential. And these are the solutions. So if you have a massive trajectory that has a mass mu, then you want its energy to mass ratio and angular momentum to mass ratio to obey these conditions in order for it to be orbiting at fixed radius r. Okay, so you just solve these 2 conditions. that'll describe something that's at fixed radius r, and this is the answer that you get. You can see why I don't want to write it on the board. I don't think it's that interesting. But everything is known. You can compute the angular velocity, which is just d phi by dt. And here, this is a massive trajectory. So before I was talking about the null light rays on the horizon. These are the time-like rays. And I just wanted to show you one thing, which is physically very important, but mathematically very gory. So it turns out you can ask, suppose I'm a massive geodesic. So I'm a time-like geodesic, and I have fixed radius, so I obey these conditions. Am I stable or not? So the question of stability is a question about whether the second derivative of the potential vanishes or not. And so in order to be stable, this tells you that you're at a minimum. So these two conditions tell you that you're sitting here. But in principle, you could also be sitting here. And so if you're here, a tiny little perturbation will make you change your radius. Right? This is the potential, and this is the radius. Radius, potential. So to ensure that you're at a stable minimum, you have to check that the second derivative is negative, I think. Yeah. And it turns out that just like this, I told you that this energy and angular momentum guarantee that these two conditions are satisfied. It turns out there's a last radius at which this condition can be satisfied. So there's a last radius at which you can be a massive particle orbiting around the black hole on a stable time-like geodesic. OK, I'm going to stop using the computer because maybe it's not helpful. I don't want to throw too much stuff at you. But let me just flash this last formula, which is RMS. So RMS, which is this hideous quantity, is the last radius at which a massive particle can be in a stable circular equatorial geodesic. That is to say, you can solve these equations and also have this condition be true. Once you go to smaller radii, it becomes unstable. So now, in the time that I have left, I want to show you a little plot that will lead me to my last topic of the day. So I wanted to explain to you why geodesics in Kerr are integrable. They're integrable because there's an extra symmetry. There's a new conserved quantity which is not obvious, but it allows you to get a fourth constant of motion, integrate the geodesic equation in first order form, reduce it to just integrating a vector field. And in your homework set, you'll be asked to derive various properties of the photon orbits, and that will lead you to understand the shadow and so forth. But now in the last 20 minutes, I want to motivate the last topic of the day, which is the existence of the so-called throw geometry when the black hole is extremal. And I think one nice way to motivate this is to draw a plot which shows what happens to various physical scales as you spin up the black hole. So here I'm going to draw A over M, which goes from 0 when you're in Schwarzschild to 1. And here I'm going to draw the Boyer-Lindquist radius r divided by m. So the ergosphere in the equatorial plane is always at 2m. Right? That's the statement that, have I deleted it? Yes. OK, so the ergosphere in the equatorial plane was always at r equals 2m, so independent of spin. OK. Now the horizon, r plus, is given here. So when the black hole is not spinning and you're in Schwarzschild, what's the radius of the horizon? 2m. What's the radius of the horizon when the black hole is maximally spinning? So A equals m. M. So the horizon radius looks like this. So it goes to 1 at maximal spin. OK, so a funny thing about this formula. So this is the last place you can have a particle on a circular stable orbit. It's horrendous, but they tell you here, when the black hole is not spinning, it's at 6m. And when the black hole has maximal spin, for the particles that are co-rotating, it's also at m. So it looks like this. So this should worry you a little bit. You should say, wait a minute, what happened? So why is this a problem? Naively. Yeah, exactly. So as Adam says, there's something funny because the horizon is a null hypersurface. So it's ruled by light rays. But what I'm telling you, what these gentlemen computed, I did not, but here's the formula, is that if you have a black hole that's spinning around some axis, here's your black hole. If you have matter that's orbiting around, it can orbit stably, so you can have a circular stable geodesic, up to some radius. So in the real world, you'll have accreting matter, you'll have an accretion disk. This matter will be nicely orbiting around. But the disk will terminate at an inner edge, which these gentlemen called RMS for marginally stable. So the last orbit which is stable. But today is more commonly known as R-ISCO, where ISCO stands for innermost stable circular orbit. So the picture is if you have equatorial matter, it can orbit at all these radii. But once you get to the ISCO, if it falls in a little bit deeper, then it cannot be on a stable circular geodesic, so it has to plunge very fast. That's the physical picture. That's why this is important. But now what you see is that as the black hole spins up, okay, the event horizon, shrinks a little bit in this coordinate picture. But you can have particles that start to orbit closer and closer and closer to the event horizon. And in these coordinates, it looks like when the black hole has exactly maximal spin, it looks like the ISCO is on the horizon. They're the same coordinate radius, r equals m. This is very bad because, as I said, the event horizon is a null surface. But now you're saying that there's a massive time-like trajectory which lies on a null hypersurface. This is an inconsistency. It's bad. Now you might say, oh, wait a second, so your coordinates are bad. This is a coordinate artifact. You're not really seeing what's happening. That is not the case. So this is a different kind of situation, which is not like the one you encounter when you're in Schwarzschild and you go to r equals 2m and you see your metric blow up. There, it's a coordinate artifact. You pick new coordinates which are smooth across the horizon, and then the problem disappears. Here, we could also pick coordinates that are smooth across the horizon. These so-called Eddington-Finkelstein coordinates exist. But if we were to look at the radius of the ISCO in those coordinates, it would also coincide with the event horizon. So this is not a coordinate artifact. It's something else. So we're missing something in this picture. So what are we missing? Or how much are we missing? Well, you can use the Kerr metric, the Kerr line element, to compute the proper distance between, say, the ISCO and the horizon. So how do you do this? You take ds along a curve that's space-like. It's going along in r. And you integrate this from some radius r1 to some radius r2. So the proper distance between two radii is obtained by integrating the line element along that direction. Okay. So what you find is that the proper distance between this radius, which is the ISCO, and this radius, which is the horizon, even though they seem to coalesce in coordinate space, so their coordinates become superimposed at maximal spin, the proper distance between these two radii is computed using the metric. So if I put r plus here for the horizon, and here I put r ISCO, this proper distance goes to infinity as the black hole spins up. So yeah, we're missing something here. In fact, we're missing an infinite amount of stuff. There's a huge amount of space that all seems contracted down to a point. And in fact, the proper distance from the ISCO to the ergosphere also diverges. So what's going on? And this paper is very nice because I think these guys really understood already in 72 what was happening. Here's roughly the plot that I was explaining. And here's the picture that explains what's really going on. Okay? So what's happened here? Let's take the equatorial plane of the black hole. So fix t and theta equals pi over 2. And now look at the equatorial plane. So if you're in flat space, this is the trampoline analogy for gravity. If you're in flat space, the equator would just be a flat sheet. If you put the sun there in the middle, it creates a depression. If you put a heavier and heavier, more dense mass, at some point you puncture the fabric of space-time, you get a black hole. And now you can ask, how deep does the hole go? And it turns out that the proper distance from the horizon to, say, the mouth of this throat, which we call the ergosphere is always at the same place. The proper distance between the event horizon and the sort of fixed radius, the ergosphere, diverges as you spin up the black hole. So on this picture, which I'm going to draw here, again, t is constant, and theta is, say, the equatorial plane, pi over 2. So we're left with the radial direction, which is increasing here. So these are circles, concentric circles of decreasing radius. And we're left with the coordinate phi that goes around them. But what this is saying is that as you spin up the black hole, you start to develop this throat. And you have all these radii, which from the perspective of somebody farther out, all of these concentric circles, all these radii are at r equals m. Right? Because where you are tells you what your radius is. They're all on top of each other. So they're all at the same coordinate, r equals m. But the distance between them can become arbitrarily large. And in fact, this throat goes on forever. It's very, very deep. This is weird. This is really weird. So this is like a crazy regime of GR. Yes?
If I start out at RMS, I can fall into the event horizon, right?
That's an excellent question. Excellent, yeah. And that takes finite time, right? So
I would expect.
It does. So that's a very good point. So remember, when you're in space-time, you can pick different locations and travel to them, between them along different directions. So if you're a particle falling into the black hole, you are probing all these radii, but you're doing so by going along a time-like direction. When I gave you that formula for computing the distance, that was along a spatial direction. So the distance between these radii along the spatial direction is infinite, but along the time-like direction is finite. And if you fall in, you feel the finite proper time that it takes to fall into the horizon. But there's physically a huge amount of space here. There's a volume which is infinite, and it's possible to throw particles in, which then orbit in here. So the ISCO is actually in here. So what I told you is that as you spin up the black hole, the ISCO becomes infinitely far away from the mouth of the throat and infinitely far away from the event horizon. So you have this very, very deep throat here. And you can have particles that are orbiting very deep in this throat. And that has many, many interesting consequences, which we're hoping some current or upcoming experiment like the Event Horizon Telescope will see. Yes?
There shouldn't be a divergent proper distance as measured by an infalling observer.
The infalling observer has a finite proper distance, which is the proper time taken for the infall, and that's finite. So along the time-like direction, it's a finite distance, but if you take a spatial slice of the universe at fixed time, there will be these surfaces which are very far away. Let me say one last thing. All these radii, from the perspective of somebody far away, they look like they're right on top of the event horizon. So this is like a very deep gravitational well. There's a little hole there, there's a well, and you think, oh, it's not so deep. And then you approach the well, and then when you look down, whoa, surprise, it's incredibly deep. Does that picture make sense? This is the picture. I'm going to write some equations which make it very precise, but I think the equations can be overwhelming, so the intuition is more important.
That was kind of getting to my question. How far down, if I took a picture of a black hole, how far down the throat can I see? Is it to the ISCO or is it to the arc boson? How far down can I see if there's something that's very close to extra now?
There are light rays that can escape from arbitrarily close to the event horizon, but then you have to ask, how much energy do they have to expand in order to escape the gravitational potential? In other words, when you climb out of this potential well, you have to pay a toll. There's an energy toll to climb out. But very surprisingly, this I think was not completely appreciated until recently. I think it's very surprising that if you have matter accreting, so the accretion disk, as you spin up the black hole, can get very close to the event horizon, and it starts to fill up this throat. So you can, and because the ISCO is infinitely far down, in the limit as the black hole spins up, you can have a ton of matter that's just sitting there down this throat and orbiting and radiating. And actually, emission from matter that's orbiting around deep in this throat is not at infinite redshift from us. So we're used to thinking that horizons are at infinite redshift, but this turns out to not be true. And the reason is that the black hole drags frames, so there's light, even though it has to pay an infinite redshift to climb out, it's also being slingshot around by the dragging of the frames of the black hole, and that gives it a Doppler boost. You know, if I take a stone and I just kind of go like, and then I slingshot it at you, it'll have a lot of energy. So the side of the black hole that's rotating towards you gives an infinite Doppler boost to the light, and that can cancel the infinite redshift, and so you can have a net effect, which is a net blue shift. So you can have very bright light that comes out of the black hole. There's a lot of crazy stuff happening, and I think this is a corner. So none of this is exotic. This is a prediction of general relativity. I haven't used any funny business, quantum mechanics, nothing. I'm just using the Einstein equations and the Kerr solution, and I'm just saying there's a special corner of parameter space, which is the regime of very high spin, where very strange, qualitatively new features can arise. And a lot of them follow from the emergence of this large deep throat. Yeah? Yes. So, okay, this is close to my research. So if you were to look at a black hole that was spinning very fast, and you were to look at it from the side, there's an opening angle of about 90 degrees. And if there was matter orbiting there, say at the ISCO or in the part of the disk that's in here, the light that you get would have redshift of order 1. In other words, it would have finite energy. You can even have a blue shift up to √3. There are lots of weird numbers that pop up. And so the expectation is if you were to look at a rapidly spinning black hole, more or less from this side, and it had an accretion disk that was radiating, including from the throat, which there's no reason why it wouldn't, then you'd get a lot of light coming out. And there's this shadow, which I talked about last time. So this is a picture of what happens in coordinate space. This is like the physical picture, but then what you see is actually very, very different. So remember last time I tried to make this point, and I told you there's a shadow, and if you look at the black hole from the side, and it has high spin, the shadow gets a vertical edge. And it turns out that all the light that you get from here arises on this line. So this line gets very, very bright. And you can compute very detailed properties of the light that you would expect to get along this line. Now, unfortunately, M87, which is the first black hole to be imaged, we're looking at almost down the barrel from above. And so if you look from higher and higher up, at some point, this line starts to close. And when you're right above, you don't see it. And we're right above M87. So we don't expect to see this for M87. But if you were to take another rapidly spinning black hole in the sky, of course, we don't know that M87 has incredibly high spin either. But if you were to find a rapidly spinning black hole in the sky and look at it from the side, you should see very bright light on this vertical edge of the shadow. It's like really weird stuff. So in other words, if you have a star that's orbiting around the black hole, in flat space, if there were no bending of light, you'd expect to see the star for half of the period when it's moving in front of the black hole, and the other half of the period it's behind, and you don't see anything. Here, the signal is literally orthogonal. Instead of the light moving horizontally, it's moving vertically along this edge, and there's always light throughout the entire period. It's very weird. It's like a whole thing to explore. OK. So to wrap up, let me quickly say a few more things about this throat, and then I'll end. So this paper that I'm showing you up there is from 1972 by Bardeen, Press, and Tucholsky. And it took over 20 years before Bardeen wrote a follow-up paper with Horowitz in which they described the actual space-time geometry of this throat by itself. And they did so in a very interesting way. So I'm going to quickly write down the equations. So what did they do? They took this line element up there, which is the Kerr geometry. And they introduced new coordinates big T, big R, big phi, which are defined by T equals big T over omega h, where this is the angular frequency of the horizon, the angular velocity of the horizon. Then they let the Boyer-Lindquist coordinate R be R plus times some small deviation big R from the horizon. And then they let phi equals big phi plus T. And so this does, what this does is go to new coordinates big phi, which are adapted to somebody co-rotating with the horizon. So when you're at big phi equals constant, you're really at phi minus omega ht equals constant. So from the perspective of somebody far away, you're exactly co-rotating at the velocity of the horizon. So these capital coordinates are adapted to somebody that's co-rotating on the horizon. Of course, we set A equals m for an extremal black hole. And now we're going to do two things. We're going to have the extreme black hole with the throat, go to these coordinates adapted with the rotation of the horizon, and now we're going to zoom into the horizon. We're going to take a scaling limit onto the horizon to basically get the geometry in this throat. That's the geometric procedure that we're following. And it's the same kind of scaling limit that you saw when Andy derived the extreme reason or nostrum metric. It's just that in Kerr, we first have to co-rotate with the black hole, and then we do the scaling. So to zoom in, we take T and R. We rescale them to T over epsilon R. And then we take epsilon to 0. So this is like performing a dilation onto the horizon because you're taking R to be smaller and smaller and smaller. And when big R gets smaller and smaller and smaller, you're getting closer and closer to the horizon. OK? So this is, I'm trying to demystify this coordinate transformation. The physics behind this is we co-rotate with a black hole, we zoom into the horizon. And if you do this, now you could do this with any black hole spacetime, Schwarzschild, non-extreme Kerr, whatever. But in general, if you do this, you get garbage. You get a metric which is, flat space, or it's degenerate. It has determinant 0. Okay, but here, because there's an actual spacetime that's living there in the throat and has infinite proper volume, you can see it as a spacetime in its own right, and you can get the geometry in this throat by this procedure. So when you take the scaling limit, there's a finite limit, and you get a good metric in the limit. And this good metric is called NEC for near horizon extreme Kerr. And it has a line element, which I'm going to quickly write down. OK, and now gamma of theta is some function, and lambda of theta is some other function. OK, so this is the geometry, the space-time geometry of this throat. So in other words, by the scaling limit, we've zoomed into the horizon. We've forgotten what's far away from the throat. We've cut it off at the mouth. And we're left only with this region, which is finally called the neck, the near horizon extreme Kerr geometry. OK? So this is a solution to the Einstein equations in its own right. You can think of this as a space-time independently of Kerr. And that's obvious because you started with a solution of the Einstein equations, and you just did a coordinate transformation and took a scaling limit. So it's always a solution. So the end result is still a solution. At large R, this is no longer flat. So large R going to infinity in this metric is going to the mouth of the throat, which is not asymptotically flat space. You're still very near the black hole. And you can see that this thing is two-dimensional anti-de Sitter space. And in fact, if you fix theta to be a constant, so you forget about d theta squared, then this metric is very close to anti-de Sitter space, the three-dimensional version, ADS3. It has this lambda factor, which is a warping factor. This is known as warped ADS3, and it arises in some interesting theories of gravity. And there's a particular angle theta, which is about 43 degrees, for which lambda is exactly 1. And so in that case, this disappears, and this is exactly three-dimensional anti-de Sitter space. So if you've taken string theory or you've been here for a while, you know that we've spent the last 20, 30 years investigating ADS-CFT, which is very interesting for many reasons, but we don't live in anti-de Sitter. The space-time that we inhabit is locally pretty flat, and on a global scale, it looks like de Sitter, which is the opposite geometry of anti-de Sitter. It's an expanding universe. But this is telling you that there are actual regions in the real world that you can travel to where space-time develops this deep throat-like geometry, which you can cut off and study as a space-time in its own right, and it's a gravitating box, just like anti-de Sitter space. And it's really out there in the sky, and now we're getting signals from it. We may be getting light from it with the Event Horizon Telescope. We may be getting gravitational waves with LIGO. So we can't travel there, but we can get signals from this. And it would be very interesting to see what we can learn and if there are signatures of the existence of this throat around real black holes. That's something that I'm very excited about.
Well, if I were to actually fall in, I would see something that would look like anti-de Sitter space, but I would only see it for a little bit before I cross the horizon.
Yes, unless you go in, if you go in such that you're co-rotating with the horizon. So there's a way to fine-tune your approach to the black hole. So for instance, if you're on the accretion disk, you're moving in radially very slowly, and you're always basically on a geodesic in free fall, co-rotating with the velocity that the black hole imposes on you. And so if you just slowly accrete on the disk, you're going to very slowly fill in the throat and spiral inwards very slowly, but you'll be in the throat for a very long time.
Okay, so it's exactly like an order pattern.
Yeah, it depends. So if you go in, if you just jump in, you pass through this very fast. This was the point that you were making before. But if you're just accreting, it's possible for you to just slowly spiral in and slow down to neck time and just stay there for a very long time. In fact, if there's a disk of matter that's slowly accreting, it's made up of stuff that's sloshing about deep in this throat for a very long time. Yeah?
Surface gravity of an extreme black hole is 0.
Yes, good. So this is another point I wanted to make. There's a formula that, next week Andy will discuss black hole thermodynamics. And you can think of the Kerr family of black holes as a statistical system that has a temperature. Of course, we don't really understand the statistical description, but in principle it exists. And you can think of the Kerr family of black holes at fixed mass as being parameterized by the spin, the rotation. But it turns out that you can equivalently think of that as being parameterized by the temperature. So there's a formula that you'll see next week that tells you the temperature of the black hole is a function of its spin. And so spinning up a black hole is really like dialing a temperature knob. And when you really spin up the black hole to this extreme regime, you're actually spinning it up to 0 temperature. Yes? I don't have a good intuition for that. I'm sure if I sat down, we could cook up some explanation. But I think that, I think it's interesting to say that naively, if you only know GR, you say that the simplest black hole is the Schwarzschild black hole, which is not rotating because it has enhanced spherical symmetry. It's perfectly spherically symmetric, so it has extra killing vectors generating the SO3 symmetry. And then you say as soon as it spins up, you break the rotational symmetry down to the U1, generating axisymmetry around the spin axis. But quantum mechanically, it's very complicated. In some sense, Schwarzschild is the most complicated black hole. And the simplest one is the extremal one, because it has 0 temperature. So in some sense, it should be the ground state of the black hole system. And okay, I only have 2 minutes left, so I want to make a final point, and I will leave you with this. The final point I want to make is that in line with this spirit that this should actually be the simplest black hole because it has 0 temperature, so it's the ground state. In fact, this is reflected in symmetry. So there are enhanced symmetries once you get into this throat. So why is that? Well, remember I said to get into this geometry, into this throat, I had to do this dilation. Now what's the infinitesimal generator of this dilation? It's generated by the vector field t dt minus r dr. So to scale into neck, I had to act with this vector field an infinite amount of times. And when you act with something infinitely many times, if you get a good limit at the end, then further acting with the same transformation no longer does anything because you've already done it infinitely many times. So further such transformations, once you get into this metric, further such transformations leave the metric invariant. And so, in fact, the infinitesimal generator of the scaling is now a symmetry. So now there's a new killing vector in this geometry, which is the generator of dilations onto the black hole. So in this picture, zooming in into the horizon, this dilation, means going to smaller radii. And going to smaller radii really means going down this cylinder. And it's obvious that this is a symmetry from this geometric picture because now you have an infinitely deep cylinder. So now you have translation symmetry up and down the cylinder. If your cylinder is infinitely deep, you can go up and down. It doesn't change anything because it's infinite. So when the black hole spins up and it develops this throat geometry, there's an emergent symmetry, which is translation up and down the throat, which is really this dilation symmetry. So we still have the stationarity of the original Kerr black hole. We also have the axisymmetry. But now there's a new vector field of dilations. And it turns out that's not the end of the story, although it's hard to really say why. But this was the Penrose diagram for the non-extremal black hole. And it had an outer event horizon R plus and an inner event horizon R minus. If you take the black hole to be extremal, the causal structure simplifies because R plus and R minus coalesce. So it turns out that this is now the Penrose diagram. It's much, much simpler. And the scaling limit that I took is basically zooming in on a thin little wedge that's going along the horizon. And this thin little wedge has a metric in here, which is the neck geometry. And if you draw the Penrose diagram for neck, then you get this. Right? It's sort of obvious. I just stretched this out. Now, this region of space-time that's right near the event horizon of the extremal black hole becomes this little patch. And if you've seen a lot of anti-de Sitter space, this is just the global strip of anti-de Sitter. And this is the Poincare patch. And I think you'll be asked in your homework to show that there's a different metric that you obtain, which is called near neck. And that one is obtained by scaling to the horizon, not for an exactly extremal black hole, but for a black hole that has a slight deviation from extremality. And if you do that, that's like zooming in on the near horizon region of a black hole that's not exactly extremal. And you get a similar metric, which is called near neck, but which has some small temperature. This will be on your homework, and it basically looks like this on the global strip. And the global strip, as you know, anti-de Sitter space has an extra symmetry. It has H plus, it has H0, and has a third one, H minus. And you can think of that symmetry as translations up and down the strip. So this is something that you need in order to go up and down the global strip. And the point is that these guys generate together an algebra which is known as SL2R. And SL2R is the global conformal group in 2 dimensions. So this throat geometry has an emergent global conformal symmetry, which is SL2R. And then there's the U1 from axisymmetry. So this is the isometry group of this spacetime. And there's an argument, which I think was first formulated by Andy, so hopefully he'll tell you about it, that says that just like in anti-de Sitter space, you can do an asymptotic symmetry group analysis, which shows that this U1 is enhanced to a Virasoro symmetry, the infinite dimensional local conformal group in 2 dimensions. And you can think of that as you go around the circle of the throat, because it's an infinitely deep cylinder, you can move lines on the cylinder past each other by different amounts. So if you have a very long cylinder, you imagine it's made up of many lines or bamboos. And you can move them past each other by different amounts as you go around the circle. And that still leaves the cylinder invariant. So you basically can enhance this to a symmetry which goes like epsilon of phi d phi, where this epsilon of phi tells you as you go around the throat how much you shift. And that is also a symmetry. And because you have a function's worth of parameters, the modes, when this guy goes like e to the in phi, give you an infinite dimensional Lie algebra, which is known as the Virasoro algebra. There's a central charge. This is a very long discussion. And then it connects to quantum gravity. So let me wrap up here. This is probably too much in one go, but this is a long story that is very exciting. I urge you to study it. The point I want to make is that when you spin up a black hole to extremality, you get this throat as an emergent symmetry. And we can think of it as a critical point, because the modern definition of phase transitions in condensed matter systems is that you pass through a critical point where there's an emergent conformal symmetry. This is exactly what happens when you get the black hole to 0 temperature. So that's the critical temperature. And then you can start to ask, does the symmetry control the approach to the critical point? And the answer is yes. It turns out that physics in this throat is very constrained by the symmetry. Everything has to be co-rotating. Magnetic fields have to obey a certain behavior, and so forth. So the symmetry controls the approach to the critical point, and there's even universal behavior. So the stuff that I told you about how you get light on the vertical edge of the shadow, that's a universal statement independent of what's going on in the throat. All the light appears on this line. So that's an example of universal critical behavior. And we're hoping that it will be some smoking gun signature of conformal symmetry in the sky. That would be very exciting. OK, I'm blabbing on. Thank you very much.